Now, you should be impressed that we have a system that can parse sentences. But maybe you're not so impressed because it only parses sentences with the word buffalo, repeated over and over. Well, all we need to do in order to handle the rest of language is to have the right grammar rules. So we could sit down and write them down ourselves. Or we can do what everybody else in the natural language processing field does, which is make undergraduates write down rules for you. Here's how it's done. At the University of Pennsylvania, they spent several years taking excerpts of the Wall Street Journal, putting it together into what's called a tree bank. And here's part of it. The tree bank takes actual Wall Street Journal sentences and asks humans to annotate their syntactic structure. So this says that in this sentence, there's a prepositional phrase starting with the word in, and then it tells you what that prepositional phrase is, an October 19th review of The Misanthrope at Chicago's Goodman Theater. And then there's a parenthetical phrase after that. That's what the Wall Street Journal writer decided to write. It says, revitalized classics take the stage in Windy City. Okay, so we're not even to the subject of the sentence yet. This was all just a locative prepositional phrase describing the subject. The subject's down here. So you can see the syntax trees for actual sentences are quite complicated, but they have the same structure that we talked about before. Each tree has a tag, and the tag expands into a bunch of branches, or a leaf, which is an actual word in the English language. And they didn't just annotate one sentence or two sentences, they annotated many. So here's Rolls-Royce Motor Cars Incorporated said it expects its U.S. sales to remain steady at about 1,200 cars in 1990. So some of this stuff is a little bit dated. But you can see the nesting of sentences within sentences within sentences, which is exactly what happens when people actually use language. So all we're going to do to build our grammar is pull out all the leaves that we see in this corpus of annotated sentences and pull out all of the expansion rules that we see. So here's one. A verb phrase can expand as a verb and a sentence. So we collect all of those, and we also count them. Now, why do we count them? Well, let me show you. Not all syntactic structures are equally common, even if multiple of them are valid. Consider this headline: Teacher strikes, idle kids. One interpretation is that this is a sentence talking about teacher strikes, when those teachers exert their rights of collective bargaining. When that happens, then the kids are left idle. So idle is a verb that means to leave idle, and the kids are the ones that have nothing to do, because the teachers are striking. Now, how can we learn something about this syntactic analysis? Well, here's all the rules that are involved in generating this, and we can look up their rule frequency per 100,000 tags that we found in our corpus. And we find that for every 100,000 S's, 25,000 of them expand as a noun phrase and then a verb phrase. For every 100,000 noun phrases, about 1,335 of them expand as a noun and then a plural noun, so teacher strikes. Most commonly, it's just a noun or a determiner in a noun, like the dog, or maybe there's an adjective in there. So there's a lot of varieties in the way that noun phrases can be structured, which is why this is a smaller number. Okay, and we'll have similar statistics for verb phrases and noun phrases, and we even have these statistics for how often it's the case that when we see a plural noun, it's the noun strikes, 25 out of 100,000 times. Using all this information together, we can figure out how likely it is that this sentence would occur at all using this syntactic structure. Now, there's a second interpretation of this sentence. Teacher strikes idle kids, where teacher's the noun and striking the children is the verb phrase. In this case, we use a different set of rules. Some of them are the same, like S expands to NPVP, but many of them are different. And in particular, we have different lexical categories for the words that are used. And we have different expansions. So we have a much more common way of expanding a noun phrase into just a single noun. That happens 4,000 out of 100,000 times. But we have a much less common way of producing the word idle, because it's more often a verb than a noun in the Wall Street Journal. So one way of choosing among different syntactic structures is just to multiply all these numbers together. And that gives you a sense of which syntactic structure uses pieces that are more common in the English language. So I'm not going to walk through all of the code that does that, but I'll show you how similar it is to what we already wrote. So on the left is the file we created. On the right is a file that loads the lexicon and the grammar from the annotated corpus that came from those University of Pennsylvania undergraduates, instead of just writing them out line by line. It also doesn't just compute the parses in any order, but it computes the most likely parses based on multiplying together the frequencies of all the rules that are used. Now, doing so is almost the same as what we had before, except for that we memoize the results and we compute only the n max trees at every time we expand, where n in this case is 1 by default, but we could compute multiple trees for each different expansion and then consider them all. This code is all the same. There's a slightly more efficient version of enumerating the different leaves. Some of the comments have changed, but basically the program is exactly what we already wrote. We also use memoization, and we compute the max trees, which are the maximum from some complete set, where we keep the n largest according to some score. And what's that score? Well, it's defined by this function that says count up the number of times that you saw the grammar use this tag with this expansion, take its logarithm, and sum those scores together. Now, summing a logarithm is the same thing as multiplying the original number. So we're just multiplying together all of the frequencies, which are what are stored in this grammar dictionary. So the result of all this is that I can run max parse and ask it for the max parses of teacher strikes idle kids. The top two interpretations are that teacher strikes idle kids, the correct one under the original interpretation, and teacher strikes the idle children, the second interpretation that we considered. And we can also get the max parses of the original sentence that we discussed. Programs must be written for people to read. Let's get 10 different alternatives for that. And after some work, it will come up with reasonable syntactic structures for this sentence. Programs must be written for people. In this case, it doesn't realize that for people to read should be all one clause, because it doesn't have enough evidence to believe that. So instead, we have to look down the list quite a ways in order to find the correct interpretation. But this one has the right structure. Programs must be written for people to read. And that's how you build a natural language parser.